All right, let's talk about a law of physics that is so fundamental, it is literally powering the device you're watching this on right now. It's Ohm's law. But what's really exciting is that we're going to explore how, at the very edge of quantum physics, scientists are finding out that even this bedrock rule, well, it can be broken.
And this whole journey, believe it or not, starts with a kind of strange question. What could a simple electrical wire possibly have in common with some bizarre, viscous quantum fluid? The answer, as you're about to see, is completely changing how we think about electricity itself.
Okay, let's dive right in. The thing about electric current is it's not some gentle little stream. You've got to picture it as a massive, chaotic swarm of charges, we're usually talking electrons here, all flowing together through a material. We're talking millions upon millions of them rushing past a single point every single second.
And the behavior of that entire swarm, it's all governed by this one beautifully simple equation, V equals I times R. This is Ohm's law. It's the elegant rule that basically dictates how everything from your toaster to your computer works. So let's quickly break down what each part really means. So first up is V for voltage. The easiest way to think about this is as electrical pressure. It's the force, the oomph, the push that gets that whole swarm of charges moving in the first place. You got no voltage, you got no push, you got no current. Simple as that.
Next, we've got I for current. This is all about the rate of the flow. It's a measure of just how many of those charges are zipping past a single point every second. The bigger the flow, well, the higher the current. And finally, that brings us to R, for resistance. This is the property of the material itself that's kind of pushing back, getting in the way, and slowing down that flow of current. Every material has a different level of resistance, and that's exactly why some things are great conductors and others are insulators.
So it all seems pretty straightforward, right? Voltage pushes, resistance opposes, and the current is just what comes out of that battle. But what's actually going on inside that wire to cause resistance in the first place? Why isn't the flow just perfectly smooth?
I love this quote, because it just puts it so perfectly. The life of a single electron moving through a wire isn't some wide-open highway. No way. It is a chaotic, bumper-to-bumper traffic jam. It's constantly bumping and crashing into things.
Here's another fantastic way to think about it. If an electric field is constantly pushing the electrons, shouldn't they just accelerate forever? Go faster and faster? Well, they don't. It's a lot like a skydiver. The constant push from gravity is eventually balanced by the drag from air resistance. For electrons, the push from the field is balanced by the drag from all those collisions. This balance creates a steady average speed, a kind of terminal velocity.
And this whole process is just pure chaos on a tiny scale. An electron gets a push, it speeds up, and then bam, it smashes right into an atom. That collision sends it flying off in some totally random direction. Then the whole cycle repeats over and over and over, trillions of times a second. And somehow, out of all that frantic, random chaos, a slow, steady, net drift in one direction emerges. That tiny drift is the electric current we measure. It's amazing.
Okay, so now that we've got our microscopic traffic jam figured out, let's throw a wrench in the works. Let's see what happens when things start to heat up, because temperature changes the game completely.
And what's so wild is that heat does completely opposite things depending on the material. In a metal, when you add heat, you make all the atoms vibrate more violently. It's like making the obstacles on the road shake around, which causes even more collisions and, you guessed it, increases the resistance. But in a semiconductor, something totally different happens. Heat actually knocks more electrons loose, creating more available charges to carry the current. This effect is so strong that it actually outweighs the extra vibrations, so the overall resistance, it decreases. So, we have this incredibly robust law, right? It explains traffic jams inside wires, it explains the weird effects of temperature, but what happens when we push it to its absolute limits? I mean, does V equals IR still work for a wire that's only a few atoms thick?
And this is where things get really interesting. We are stepping beyond the familiar textbook physics and right into the frontier. It's time to see what happens when we actually break Ohm's law.
You know, for the longest time, the answer seemed to be a resounding yes. This law is universal. In fact, there was a landmark study back in 2012, published in Science, that showed the law holds up incredibly well, even for tiny silicon wires just a few atoms wide. Its strength was just astounding.
But that's the thing about physicists, right? That very robustness just made them want to push even harder. And they found that if you take an extremely pure material, you get it incredibly cold, like close to absolute zero, and you channel the electrons through very narrow paths, the old rules start to bend. The very nature of the traffic jam begins to change.
And here is the absolute key difference. In normal, everyday ohmic flow, the electrons are mostly colliding with the atoms of the wire. They're acting like individual cars in traffic, each on its own journey. But in this new, bizarre regime, the electrons start colliding with each other so often that they stop behaving like individuals at all. They start moving together, collectively, more like water flowing smoothly through a pipe.
Scientists have a pretty cool name for this. They call it hydrodynamic electron flow. It's this special state where the entire swarm of electrons starts to behave like a single thick, viscous quantum fluid. They aren't just a crowd of individuals anymore, they're a single flowing entity.
So how on earth do we even know this is really happening? I mean, it's not like you can zoom in and watch them, right? Well, recent discoveries have found this incredible, unique signature. As the electrons start flowing like a fluid, scientists can actually measure an unexpected voltage that appears sideways to the main current. The appearance of this transverse voltage is the smoking gun. It is a clear, undeniable hallmark of new physics, something Ohm's law could never, ever predict. And that brings us right back to where we started. That simple wire and that quantum fluid, they have way more in common than we ever thought possible. And it leaves us with this one final mind-bending question. If electrons can spontaneously organize themselves into a collective fluid, breaking one of the most fundamental rules of physics, what other quantum weirdness is still out there, just hiding in the materials we use every single day?